Okay, now we'll be discussing Article 29.3 of Survey and Jude, that is law on a current loop in a uniform magnetic field. We have already seen that tau is defined as the turning effect of a body and it depends upon the force and the moment arm. Now, in this case, we have a rectangular loop with current I moving in the given direction, that is the counterclockwise direction. We have divided this rectangular loop into four segments, that is 1, 2, 3 and 4. We have magnetic field, that is uniform magnetic field, and the direction of the field is given. Let one side of this rectangular loop be represented by A and the other one is represented by B. So if we look at this figure closely, we'll see that the direction of the magnetic field and the length of one segment and segment 3, they are parallel to one another. So from the formula that we have seen in article 29.2, it says that I into L cross B. So when we have a cross product, it means that we will be having sine of theta when we simplify this equation. So sine of 180 as well as sine of 0 will give us 0. So these two segments, that is segment 1 and 3, they will not contribute to the magnetic force, whereas segment 2 and 4, they will be contributing to magnetic force. As if I want to find the magnitude of this magnetic force, I will simply write F2 equals to current through segment 2, and the length of the segment 2 is given by A, and this is B, the magnetic field, and sine is if the field is in this direction and the current and the length element is in this direction, so it will be 270. But as I am considering the mod over here, so magnitude will give me a positive value, so I can write IAB. Similarly for segment 4, the magnetic force will also be equals to IAB. So these two segments will contribute to the magnetic force, and the direction of these forces opposite to one another and are equal, but they will produce a turning effect in this rectangular loop. So what will happen over here, that this is what we have calculated by looking at the figure, and if we further proceed to the turning effect, that is the tau, we know that tau is equals to Fr sine of theta, where F is the force, R is the moment arm. So when we have this rectangular loop over here, and one force is in this direction and the other one is in this direction, and if I join these, the midpoint is represented by O. So the width of the loop is given by B. So if this is the center of this width, so this will be B by 2, and again this side will give me B by 2. So from here, if I see that this force is in this direction and this will be the moment arm, which will help in producing the turning effect, that is tau. So if you look at the figure 2 over here, this clearly shows that this force is in this direction, F4 is in this direction, and we have the moment arm B by 2, and the turning effect is produced in this direction in the presence of uniform magnetic field. So if now I put in the values for F and R, and to find the maximum tau, I can write F2 into B over 2, plus F4 into B over 2. Putting in the values for F2 and F4, I can write IAB B over 2 plus IAB B over 2, and summing them up will give me IAB into capital B, where where this AB gives me the area of rectangle, that is both sides. If I multiply these two sides, I get the area of rectangle, and I can write this maximum tau as I capital A into capital B. So tau can be written as IAB, where A is vector over here and it has a certain direction. From here I can introduce another parameter which is known as magnetic dipole moment, and this magnetic dipole moment is represented by mu, and it is a vector quantity. It has the same direction as the direction of the area, and now I can write this tau as tau equals to mu cross B. If we have n number of loops, to calculate tau, we have to introduce these number of loops in the equation as well, and we can get n IAB. And if you want to calculate the potential energy of the magnetic dipole in a magnetic field, we will simply write U equals to minus mu dot B, which is a scalar quantity, and we can easily find the potential energy by using this equation. Okay, now we'll be discussing example 29.3, which is related to article 29.3. uh, we have a rectangular coil of dimension 5.4 centimeter into 8.5 centimeter, consists of 25 turns of wire and carries a current of 15 milliamps. So this will give me the area. These are number of turns, and this is I, and 0.350 Tesla, that is the magnetic field, is applied parallel to the plane of the loop. We have two parts. A, calculate the magnitude of its magnetic dipole moment, that is we have to find mu, and what is the magnitude of the tau acting on the loop, so we have to find tau. Data is A. I have simplified the given value, and area is 45.9 to 10 to the minus 4 meter square. Number of turns, current in milliamps, it was given in milliamps and I have converted into amps, that is 15 into 10 to the minus 3 amperes. Now I have to find the magnetic dipole moment. For that, simply use this equation, that is mu equals to NIA. Putting in the values, the value for mu will be 1.72 into 10 to the minus 3 amperes meter square. For part B, we have to find tau. Simply write tau equals to mu B, putting in the values, and the value for tau will be 6.02 into 10 to the minus 4 Newton meters.